Okay, so I think let us start. The recording is in progress. Good. Okay, so today we finally start higher dimensional hyperbolic spaces. Okay, now I think just before we start, I will give a few theorems which we are going to use. So the first one is, so it's like flashbacks from Riemannian geometry. First of all, I want to give the following theorem. Let M G be a Riemannian manifold. P be at any point in M, and V be a vector from TPM. Then there exists a unique geodesic. Then there exists a unique maximal geodesic. Maximal geodesic gamma from I to M, such that zero is an interior point. So zero is definitely a subinterval of R, right? Some interval in R. Zero is an interior point of I, just in case. Gamma of zero is P, and gamma prime of zero is V. So geometrically, it means that if you fix a point and the tangent vector, right? So this is P, this is V, then there exists a unique geodesic in this direction passing through this point, right? The word maximal here means that there is no larger interval J containing I, right? Such that gamma from J to R is also a geodesic. Yeah. This is the word maximal, and we will be using this to describe a geodesic. Yeah. Oh yeah, sure. Thanks. It should be gamma from J to M. And okay, so again, it's like in RD, you definitely have the unique geodesic, right? So a very simple example. In RD, so basically two examples. In RD, we just simply have P plus TV, right? This is our geodesic. On the sphere as, okay, D minus one sitting in RD, we know that for any, so suppose this is point P, right? And the tangent vector V. Locally, right, we can like take a geodesic in this direction and that, or in some minor segment. But since I have this word maximal here, the maximal geodesic will be the entire great circle, right? This will be my unique maximal geodesic on the sphere. So let me take another color. So this will be my unique geodesic. Okay. Then, in fact, one can also actually parameterize them using just cosines and sines. Yeah, this is my unique maximal geodesic given the point P and the vector V. Okay, so in general, since we are going now to consider higher dimensions, we can think of something like, so we in Euclidean geometry, we have planes and hyperplanes, right? And I actually want to, are there any similar objects in general higher dimensional Riemannian manifolds? And in fact, there are. I can define
I have a subset of R. I will be R.
where?
For your definition of
Yeah, in general it will be R. Yeah, but it's but it will be, it is basically the Hopf-Rinow theorem. I need the Riemannian manifold to be complete. Then I know that any geodesic can be extended to a real line R. Yeah. Okay. And yeah, I will mention this theorem actually soon. So okay, a submanifold N in M is called, okay, actually I need to define embedded and immersed first, probably, right? Okay, so a submanifold okay, I will say first what I wanted to say. So it's called totally geodesic. Sometimes it's said to be a totally geodesic subspace if any geodesic in N can be extended to a geodesic in the ambient manifold M. So definitely one-dimensional lines, planes, and so on are totally geodesic subspaces in RG, right? So totally geodesic subspaces, again, examples. I can take any affine planes, right, in RG, and those can be identified with some RK, where K is less than D. Okay, and it can be actually even zero, right, since I can take a point. But well, in fact, I can take actually here also less than or equal, but I'm interested in proper, totally geodesic subspaces. Since we also know about spheres, so I can say that sections. Okay, how to call them? Okay, the subspheres, right? Subspheres. As K in SD, but not all, but those that are obtained by sections, by planes passing through the origin. Yeah. So subspheres obtained by obtained by sections. Okay, obtained as intersections of SD with linear subspaces of RD plus 1. Yeah. And definitely I need an example of something not totally geodesic. Not totally geodesic. Obviously the sphere S2 is not a totally geodesic in R3, right? It's a submanifold of dimension 2. Very nice, embedded, but geodesics in S2 are never even close to be geodesics in R3. Another example, which is already a little bit more subtle, so I can take sphere S2, right? So this is totally geodesic. Totally geodesic. But if I take another circle, we just, so a slice, again, another section by, so they simply move and affine, and I'm taking now an affine plane, hyperplane parallel to the, like this equatorial section. I will also obtain a circle, right? But it is not a totally geodesic embedding. So it will be, so this embedding, right? So this is S1 as well, right? And this is S1. But this is already not totally geodesic. Okay, now I think it's time to say something about, I wanted to say something about embeddings. So okay, so let M and N, so far these are just smooth manifolds, be smooth manifolds. F, okay, yeah, I prefer to take F from N to M is a smooth map. Then F is called an immersion. Okay, it is called an immersion if the differential at every point so if dx of f, okay, so what it should be a non-degenerate linear map, right? It should be like, it should be just of, it should be of maximal rank. Yeah, I want to say it should have like trivial kernel, but it's the same. Yeah. If so it's a linear is a linear map of maximal rank. Obviously, this implies that the dimension, so my matrix, it's a matrix, so the dimension of n is less than or equal than the dimension of m, right?
Saying it is maximum. Yeah, that's that. Probably. That's the way to say it.
And f is an embedding if f, well, is an immersion, obviously, and in fact, it's a diffeomorphism with the image. Yeah, so I would say n is diffeomorphic to its image in M, right? This in particular, okay, the fact that it is diffeomorphic to the image, say, being a submanifold in M, probably implies that it's immersion, but what is interesting that basically immersions, what is like the main difference between immersions and embeddings, that immersions allow self-intersections. Yeah. So the remark. It's better to say it's like so okay, it's like, I know it's like a remark, but not a very good remark. I would say roughly embeddings are immersions without self-intersections. Yeah, so but to be honest, I don't remember what is under what conditions it is true. So if I take a smooth map, which is a bijection with its image, and if it is an immersion, maybe it's still not enough. I'm not sure.
There's things where you can have like an interval that sort of approaches.
Yeah.
Itself. That's bad.
Yeah. So yeah, probably it's okay. I will check. I mean, maybe I will say something about this, but later. Right now, what is important, that just the intuition behind that, right, is that we do not want self-intersections if we were talking about embeddings. Okay, and I think I would take an example on the torus, two-dimensional torus. But like right here, circles are certainly embedded totally geodesic. Well, great circles are embedded totally geodesic subspaces, right? And the manifolds. So, for instance, this one, right? This one is also an embedded submanifold here. Actually, let's start with the sphere. Yeah, examples. So I'm taking the picture. Yeah, so I have like two inclusions of S1. So F and I don't know, another map H. Again, two pictures. So this one is, so this one is the blue one, right? And here is the orange one. And this is totally geodesic. Sorry, this one is totally geodesic embedding. This is not totally geodesic, but it's still a submanifold, which is like S1, right? But one can take something like weird here. I don't know, let me try to just draw some random curve. Which is with self-intersection here, right? I don't know, and where can I can actually go, yeah. Oh, maybe I can just, yeah, it's enough. It's also a submanifold, right? But it's, okay, what is it actually? I guess it's a self-intersection. So it's also a circle, right? But it's already an immersed circle. So this orange is, yeah, an immersed S1 in S2. Yeah, and you can take, you can also like draw a picture of a torus, and then, so actually the example number 3. Okay, let me draw it here. I think I have enough space. So I'm taking a square, and this is my torus, right? So if I decide to take, I can just start drawing, I guess, lines, right? So if I take this line, then that one, so just draw several lines with by changing the angle, yeah. Then I will definitely obtain, well, some of, for example, this one will be a simple closed curve, I guess, without self-intersections. Let us think. So we first identify, right? We first identify this. Yeah, and I don't know. It will probably look something like that. Yeah, but wait, I'm not sure. Yeah, it will probably wrap around the cylinder. Yeah. So most likely it's actually something like that. But if I change the angle, I can obtain some more weird already with the, I don't know, it's kind of something like that. Wait. So it goes that way under, then down, then again up, right? Okay, I will just right here. Yeah. So it can still be embedded, but at some point it will already make self-intersections. Yeah. Or it's not true. Let us think. So these are all still embedded, right?
It's like this.
The point is that if the angle is irrational, then I will just get irrational winning of a torus, which will be like everywhere dense. Yeah. And it will not be already, it will be still immersion, but it will not be already a proper immersion. So yeah, that's the thing. But those are embedded. I want to get something with self-intersection, but probably to make self-intersection, I need to. Okay, basically what I need? I need to get the line right here such that its image intersects. Yeah, I'm not sure if I will get that. Yeah. Yeah, probably I will not. Yeah, probably I will not. At least I will not get a geodesic, right? I will not get a geodesic with self-intersection here.
Yes.
Yeah. But I can definitely draw again anything with self-intersections like here. It will be just not a geodesic immersion. Yeah, that's particularly nice. So again, you see here on the sphere, we also do not have geodesics with self-intersections. Yeah.
Those curves we've drawn on the geodesics and flat metric on the torus.
Yeah, sure. So let me, indeed. So embedded geodesics with respect to flat metric. Flat metric. Flat meaning it comes from Euclidean geometry. So we technically do not embed this torus as a subspace as a submanifold in R3, right? It's only a topological picture. So geometrical picture is basically here. If you want to see geodesics on the square, the best picture, I guess, is just to draw a square on the plane and look on the geodesic lines in R2. Okay, so this is about embeddings and so on. But now I think I want just to mention the last important theorem we will need. So theorem, it is hoped, theorem, let M G be a Riemannian manifold and let rho be the distance or metric, be the associated distance function. Then the following are equivalent. Following are equivalent. M is a complete metric space, which means that every Cauchy sequence has a limit. Sequence of points in M, right? Okay, let it be Pn. Okay, converges to some P in M. The second is that M is geodesically complete. Which means that every geodesic gamma from I to M can be extended to gamma from the real line to M, like to a geodetic. Yeah, so any geodetic from, okay, technically I should probably write gamma tilde. Sorry, and this contains our interval I, right? But there is also the third condition. Any compact subset in M should be closed and bounded. Yeah. Oh, sorry, any compact. Okay, in M. Is closed and bounded. In particular, so if those are true, so if like these conditions hold, then, well, any of these conditions hold, then in fact, for every 2 points, there exists a geodesic realizing the distance. Yeah. So as a corollary, if it is a complete, so let me move to the right part. Okay, I would say like, yeah, moreover, if M is complete, then for any 2 points P and Q in M, there exists a geodesic gamma joining P and Q such that, yeah, the distance between P and Q is precisely equal to the length, okay, to L of gamma on 0 to 1, okay? Well, where gamma of 0 is P and gamma of 1. So it will be my gamma of 0, gamma of 1. So just, huh? Oh, yeah.
They should always be bounded. Same sort of part.
Yeah, sure. Any closed and bounded. Any closed and bounded is, okay, I will just check, okay? But probably you're right. And yeah, I wanted just to say, like, if M, okay, the remark, if M is complete, P is the point in M, then definitely M without P is not complete. Right? Since if you remove a point which is a limit of some Cauchy sequence, then definitely you'll get something non-complete. Okay. Yeah, yes, and the problem will be with those geodesics that pass through this point, right? And then it's a problem, since then you cannot extend this geodesic. Okay. Yeah, I wanted just to check just in case the statement of the Hofrinov theorem, but yeah, so we will mostly deal with complete Riemannian manifolds. Yeah, I think that you're right. I cannot find it, but I think that yeah, in fact, in this case, if and only if holds, right?
Yeah.
In this case, the if and only if holds.
PDF has it that's close to
so,
that applies to
yeah.
that.
Yeah. So I would say that K, yeah, let me indeed be careful here. So K is compact in M if K, sorry, if and only if K is closed and bounded. Yeah. If and only if should be here. Yeah, that's correct. Indeed, you're right. In one direction is kind of clear, but what I meant to say is yeah, indeed, yeah, I found it now. Yeah, so the reverse direction was actually like generally it is not true. Yeah, generally it is not true. Okay, yeah. So now I have I can already start higher dimensional hyperbolic spaces, and so let me use the new board. Okay, finally, hyperbolic spaces HD. We will have, so usually it is written like that, but I will not, yeah, I will skip this second bar. And so, yeah, I will write it just simply HD. We will have, we will consider four models. Four models. And those four are these. Okay, hyperboloid model, hyperboloid model. I will denote it as like HD this way. Then projective Klein model. KD. Number 3 is the ball model, the Poincaré ball model, which I will also denote as BD, as we discussed in dimension 2. And finally, the upper half space model. UD, right? So the four models. Sometimes people also consider the fifth model, which is based on the hemisphere, yeah, on the hemisphere. But this model is kind of like I don't know, it's like it's a stop on the journey from one model to another. We will not really use it. It's not so convenient. To be honest, the model number 2 usually will not be like that useful for us, but it's like still an important model to know. We will mostly use the models number 1 and 3 and 4, and the most popular are number 4 and number 1. Number 4 is especially popular in dimensions 2 and 3, while in higher dimensions both are used. And the model number 1, the hyperboloid model, sometimes it's called vector model, allows to work with like linear algebra, convex polyhedra, and so on, which is very useful. Okay, so I will start with the hyperboloid model, and I will probably draw a picture and just simply explain how it looks like, and then we will make a break. So the hyperboloid model, now it's the hyperboloid model. Let R D1 be the Minkowski space of signature D1, which means that Minkowski space, so that is it is RD plus 1 equipped with a with an inner product or with a scalar product of signature D1. You can take any form, definitive signature and D1, but over R, these are all equivalent to one certain form. So to an inner with interval signature in one. We usually take the following form. Sometimes I will denote it by fd, 1 of x, but usually I prefer just to write x, x in brackets. And this is, so the quadratic form associated with this inner product is given by that. It's minus x0 squared plus x1 squared plus, and so on, xd squared, right? So that is the scalar product between two vectors in the matrix form, right, can be written as follows. I'm taking x transpose I d comma 1 y, right, where I d comma 1 is the diagonal matrix minus 1, and other are ones on the diagonal. Yeah. So this is my form. Definitely this is a column, right? And this is a, oh yeah, and this is my d plus 1. So the matrix, it is a matrix of the size d plus 1 times d plus 1. Yeah. So this looks like that. Okay. And I will just define HD here. Okay, I think on this side. Then HD is defined as follows. We take the points x in RD1 in the Minkowski space such that the scalar product of x with itself is minus 1, but I want to take also the connected component of this. And the pictures here, I have the cone, this is 0, and I also have this, well, it's quadric, right? Well, it's not quadric, but it's, so it's like submanifold in RG1 having two connected components. And this is my HD, right? HD is right here. It is the upper, like, yeah, the upper half sheet of the hyperboloid. And the points are just basically the vectors with this satisfying, right, this equation having And the axis, yeah, the axis x0. So this is basically the axis x0, and my other axes are somewhere there. Yeah, they're outside of the cone. This white cone, it is also actually a nice cone. It is the isotropic cone. So the blue vectors satisfy that the square x squared is equal to 0, right? The scalar product of x with itself is equal to 0. Okay, I think, yeah, I'm going already to make a break. But so what we will do next? We will find out what the tangent planes are to this submanifold here, right, to this space HD. We will define the metric, and again, we will see what are geodesics, what are geodesic planes, isometries, and so on. The plan is to go, first briefly go through all 4 modules, and maybe I will just write down metrics and so on. Then we will talk about reflections, isometries, and so on. And again, in all 4 modules. And so we kind of we will be working around those 4 modules and discussing different objects. Okay, so let's now make a break. 10 minutes break, yeah. Okay, so we continue the hyperbolic model. Yeah.
Talk about complete metrics.
Mm-hmm.
Complete is a modifier on the Riemannian metric, not on the manifold. So if M is complete with a given metric, if you delete a point, it's not complete with respect to the same metric. But
Yes.
you can put a metric on it. If you're willing to change the metric, you can make it complete again. Just sort of take that point that you've excised and you push it to an end.
Yeah. Yes. Yeah, that's true. So in fact, here it's important that here M without P is not complete with respect to the same metric. Yeah, that's right. Complete with respect to the same metric, I would say GM, right? Okay. So here we defined the hyperboloid. I took the upper component, so it's a two component manifold, right? Now I would like to take in fact the tangent space of HG is just the set of all vectors y in R D1, right, such that the scalar product x and y is 0. Okay, and in fact, it's already enough to define the metric. I will probably do it this way. So since I introduced the language of Riemannian manifolds, let me just take, so it should be the restriction of the Lorentzian. Yeah, by the way, this is sometimes called the Lorentzian scalar product. Yeah. And actually, this RD1 is also sometimes called the Lorentzian space, but I don't know. I'm just used to this this terminology. Okay, so then the metric we define, right? We define a hyperbolic metric I will denote it as just GH as restriction of, okay, I will, I think I will just write this, right, on, in fact, on the tangent bundle. So we define a hyperbolic metric GH as a restriction on the tangent bundle of HD, okay? Well, I would say that this is an exercise. So, okay, from now on, we are moving already a little bit in a bit more faster, I would say, manner, and it will be, so our material now is going to be a little bit more advanced. So I will just leave an exercise. I actually plan to collect those exercises I'm leaving. Show that this is indeed a Riemannian metric. Is indeed a Riemannian metric. Okay. But just to remind you, it's already symmetric form. So basically what you need to prove that it is positive definite when once you restrict it on the tangent space px hd, right? And this can be done in just explicitly. Okay, now I want to say the following. So what are, with respect to this metric, what are my geodesics and geodesic submanifolds? And the following theorem actually holds. So okay, so geodesics, we start from that. Geodesics in HD are simply the sections of, so are obtained as intersections of two-dimensional planes in RD1 with H. Moreover, you can just take, so you take hyperboloids, right? You take a vector, suppose you take a point P, and then a vector, the tangent vector V. Then your tangent vector can be like drawn here, and this is another, so this is your vector P, and this is the tangent vector V, right? I kind of draw them equal, just with different starting and end points, yeah. And then I just take the linear subspace spanned by these two vectors V and P, and I will get something in the intersection. So it will be actually it will be hyperbola from our like Euclidean point of view. It will be just a hyperbola, right? And the way one can show that actually one can parameterize the geodesics. So I can write that this geodesic will be written in terms of cosines. Okay, I will write and then check. hyperbolic cosine of S P plus the hyperbolic sine of S multiplied by V, probably, but let me check, okay? I'm not 100% sure I remember this correctly. Yeah, I think that's true. Yeah, that's correct. Okay, the second part of this theorem. So we obtain such hyperbolas, right? Definitely you can parameterize them like using just hyperbolic cosine and sine. But I wanted to parameterize them specifically in this model. Yeah, that's the point. The second part is about higher dimensional, so totally geodesic subspaces. Okay, so of dimension K are simply the are in fact, isometric, yeah, are in fact HKs. Some are in fact equivalent, can be identified with HK sitting in HD, right? Obtained by, obtained as intersections of some plane U with HD, right? Where U is K plus 1 dimensional plane, yeah? Dimension of U is K plus 1. So again, the idea is the same. You just take higher dimensional space and you intersect the hyperboloid with some higher dimensional linear subspace. So this is again a linear subspace. By the way, here I also should write of two-dimensional planes in the sense of linear algebra. So of linear two-dimensional planes, right? Of linear two-dimensional planes in RD1. So it is important that all our planes pass through the origin. Okay, there is a hint to prove. Well, first you need to prove this, and then later already it's easier to show the second part. By the way, as a corollary of the first part, corollary so the first part implies that the distance, yes, the distance rho h satisfies the following identity. The hyperbolic cosine of distance between any two points x and y is equal just to minus x and y. It's a very simple and short formula. So if you want to compute the distance between any two points, so you have just two vectors, you just simply need to take the negative scalar product and then take the hyperbolic cosine inverse, and this will give you this distance. It follows precisely from this, like I would say almost immediately. And yeah, in fact, I'm going to use this formula to, so when we will move from this model to all other models, it will be quite helpful, since then it will allow us to compute other metrics in other models. Okay, so what is the hint to this, to proof of this theorem? And the hint is the following. One can notice that actually reflections one can consider reflections in hyperplanes. Let me move. I think I will not move. I will just erase here. And this proof requires some isometries. And so hint to part one. Let E be any vector RD1 in RD1 such that E times E is, okay, we can make it, we can take it to be normalized, but what is important is positive, right? So, sorry, in my picture, it means the following. I have the hyperboloid and my vector E is outside of this cone, yeah? And then the reflection RE, the reflection RE, which is defined as RE of X, it sends X to minus 2 EX over E times E, and this is multiplied by E, but usually we normalize it to make it to be equal to 1, right? Then the reflection is an isometry, of HD, right? So you first need to prove that this is an isometry. But the fact that this is an isometry immediately follows from the definition. You can just compute what you need is just take X and Y, right? Since the Riemannian metric is obtained as the restriction of the scalar product of X and Y onto the tangent plane, you basically just show that the scalar product is invariant with respect to this reflection, right? So what you need to show that X product Y is equal to, right? So one just needs to show that XY is equal to RE of X product RE of Y, okay? And that's enough to show that it's an isometry. Okay, then one uses another, the following trick. Since it's an isometry, it certainly sends geodesic to geodesic. And then you take hyperplane passing through P and V. And then you take the reflection with respect to this hyperplane. And you can just say that, okay, let me parameterize this as gamma of S, right? Let it be just some curve. And you use the fact that for any vector and point, you have a unique geodesic passing from P to V, right? And this is kind of like a symmetricity trick, gives you the, it eventually implies that the geodesic should coincide with this curve, okay? But this is a hint, so I'm just writing then use, okay, then apply this reflection to, okay, in the situation when P belongs to HE and V also belongs to, okay, yeah, V also belongs to HE, right? Yeah, by the way, I did not, is an isometry of HE, but I didn't define HE. So let me write it this way. So it's an isometry of HD, which fixes HE, which is the set of all X in RG1, such that the scalar product of X and E is 0, right? So which fixes this hyperplane pointwise. Yeah, it's actually pointwise. Yeah. Okay. So and then you apply this reflection in the situation when P belongs to HE and V belongs to HE, and use the theorem about uniqueness of a of a geodesic through P along the tangent vector V, right? Basically, that's the idea. After this hint, it's already not that hard to work out the details, yeah? Okay, then after that, you can show that, in fact, this hyperplane is a, so in fact, this then implies that this hyperplane is just codimension 1 totally geodesic hyperplane in HD. So it can be identified with HD minus 1, right? This hyperplane can be identified with the HD minus 1. Okay, so this is very nice. So in fact, in this model, our geodesics are associated with a fine, okay, with just linear hyperplanes and RD1. We will talk about isometries a bit later, but this was like the first, so one of the, this is actually a very important type of isometry, since again, any isometry, we will eventually see that any isometry can be generated by at most n+1 reflections in hyperplanes. Yeah, well, it can be decomposed into the product of at most n+1 reflections. Okay, now I want to say something about other models of the hyperbolic space, and I will need a picture. Okay, I do not want. Okay, let me. I will not erase all this. Let me now come to the left side. So now I need to do a large picture showing how to obtain all other models. Okay, so I have this hyperbola. Okay, so this is my HD, right? Okay, it should be like calligraphic HD, but sometimes it's not, but it's okay. So then I obtain, I can consider actually a few hyperplanes. One hyperplane is this, and this is a hyperplane x0 is 0, right? Since it passes through the origin. here is my axis x0, right? And there are some other, all other axes are contained in this hyperplane actually. Okay, that's nice. Now I will take another hyperplane, level 1 hyperplane, and this is kind of an affine chart here. And so it like passes through this pole of the hyperboloid, right? And in fact, since I have two symmetric, right? I have two symmetric, I have another pole right here. Right now it will be an important. So these 2 points are important for us. This one, and so this is the point like 1, 0, 0, and this is the point -1, 0, 0, 0, right? Okay, so the first model is obtained as a central projection from the origin. So I will, okay, I want to draw a nice picture. So this is a disk. Okay, it's the ball. This ball, BD, right, is obtained as follows. I am taking just the central projection. So I take any point x from the hyperboloid. I draw a ray, like, okay, a ray containing, well, starting at the origin and passing through x. And then I take the intersection of this ray, of this line, with the hyperplane x0 equals 1. It is kind of geometrically obvious that the entire hyperboloid will be sent to the unit ball BD inside this, right? Oh, sorry, I wanted to define this actually as KD. Yeah, it's KD. So it's important. It's the projective fine model, right? So my point X from AG, it is sent to like the point which has the coordinates 1 and some, I don't know, X. Let it be X. How should I go, like X hat? Yeah. Sitting in KD. And obviously the Euclidean norm of X hat is strictly less than 1. Okay, there is another model, which is also the unit ball. So I will now draw the ball. Okay, let it also be, I think, orange. Why not? So it's going to be, now it's indeed the ball BD, and the projection from this model, to the ball model BD, goes, well, it shouldn't be the orthogonal projection, it's another projection, and it goes this way. I am taking the same point X, but now I'm taking the ray from this, I would say, like south pole. Actually, yeah, this should be the south pole, right, of the hyperboloid. And I'm drawing this line, and where intersects my hyperplane x0 equals 0, I'm getting the image of X inside BD, right? So now I have another projection to the point 0, x, I don't know, just bar sitting in VD. So eventually I identified with, and also the Euclidean norm is less than 1. It's less than 1 since you still have, like, you can draw, well, I'm not going to like really draw this, but you can imagine that you have the cone parallel to this isotropic cone, right? Certainly, if your rays go that way, you do not intersect it with HD. And if your ray is like any, like you have any epsilon, I don't know, like this, not like distortion, but if you move it slightly inside of this cone, you already get some intersection with HD, right? So again, your entire hyperboloid will be projected down to this unit ball. And what is interesting that this isotropic cone under both projections can be sent to the boundary of the ball. This Klein model is useful because of the following, actually. One can think of isotropic vectors having positive x0. One can think of them as the ideal boundary. So the ideal boundary of HD, it is, what is it? It is the projectivization of the cone, but with respect to positive numbers. So I would say it is the cone C, its quotient by R greater than 0, right? Something like that. I think I can write down. But the point is that I'm taking the non-zero elements. Yeah, so where C consists of non-zero isotropic vectors. This is my cone, and I'm taking its quotient. Wait, is it true? Maybe I still should take the connected component. Yeah, I still should take, I will write C plus, where x0 is still greater than 0, right? Probably this is, yeah, this, I should do this. Well, actually, if x0 is not 0, then I do not need this. Yeah, correct? Okay, yeah, so we will talk about the ideal boundary a bit later, but what is interesting that this cone is projected just to KD, so the this ideal boundaries will be just n minus 1 dimensional sphere, right? And same here. So this ball projective Klein model is particularly useful to show that the compactification of the hyperbolic space is just the closed unit ball, right? So the topology of the compactified hyperbolic space is like a topology of the Euclidean ball, but geometry on infinity, I mean, we do not like have any geometry on infinity associated to the hyperbolic metric. Well, okay, one can do something, yeah, but it's not, I mean that the standard spherical geometry is not related to hyperbolic geometry inside the ball, yeah. Okay, so this picture shows how to get from the hyperboloid model to to the Klein model, and so this is Klein, and that's why it's K, and this is a ball, and that's why it's a B, and there is the fourth remaining model. Well, we already discussed how to pass from BD to the upper half space model. So let me now draw this picture separately. So this visualization is two-dimensional, right? Not really helpful in how to understand the geometry of dimensions starting 3, but I will try to draw it here. So let me now take B3. So now my B3 is here. I'm drawing the three-dimensional ball, unit ball. So my points are inside the ball, right? The points, and this is S2, which is the ideal boundary of B3. But what I want to do is to take the upper half plane. No, I wanted to. So this is my. So I want to construct the upper half plane, right? U3. Well, in fact, I explained this in dimension 2. We applied an inversion with respect to a circle of some like very nice circle, which was defined based on the fact that, well, basically the radical, this boundary was the radical axis of two circles. Actually, the notion of radical axis can be extended to higher dimensions. I can consider two spheres, and I can take two. So if I have two spheres in Euclidean space, I can find the set of all points x such that the degree with respect to one sphere is equal to the degree with respect to another sphere. If the point is outside of the spheres, it means that basically the tangent Euclidean segments from x to this sphere is equal to the length of the tangent segment to another sphere, right? So the degree means that this tangent is equal to this, right? Okay, it is known that this set will be a hyperplane orthogonal to the center segment, to the segment of centers, joining to centers. So here I will just take the sphere so its center is going to be the south pole of my sphere S2, and it's going to pass through well, basically, it's going to have the radius square root of 2 again, and it's going to intersect this yellow sphere precisely in this circle, yeah? So my sphere looks like that. Let me denote the sphere as, I don't know, large omega, right? It's yeah, it is also, okay, it can be identified as with S2, but it is another sphere. And so what I am saying is that the inversion with respect to inversion defined precisely in the same along the same lines as the inversion in two-dimension in dimension 2, it gives me a Riemannian isometry from B3 to U3, right? As a Riemannian isometry. As well as those two projections are also Riemannian isometries, right? So this projection and these projections both are Riemannian isometries. So the idea is that we take we now start with the hyperboloid model, and we choose the Riemannian metric over there, and then we apply it to maps, and we just, I don't know how to say that, translate this Riemannian metric. It's not a push, it's push forward, yeah, basically. Well,
It's nice.
yeah, it's not isomorphism, yeah. So we kind of make this push forward of the Riemannian metric from hyperboloid to other models. So the idea is that from this model you can come here, you can come here, and from the ball model, these two models are conformal. So okay, again, the pictures. I think that let me just give some pictures. What are the, by the way, what are the geodesic subspaces? So this is quite important, and this is what I should mention. So geodesics here are just Euclidean lines or Euclidean planes in the ball, right? I think I should better write it down here. Okay, so geodesic, totally geodesic subspaces in my models. So in KD, any Euclidean chord, but just with another metric, or, right, it can be any plane not necessarily passing through the origin, of course. But the metric is not Euclidean. It can be computed using, okay, there will be another formula using the hyperbolic cosine, but there is also an interesting formula using the logarithm of the cross ratio of 4 points, including the points on the boundary, but we will discuss later, okay? So this is the Klein model. In the ball model, these all are circles or spheres orthogonal to the boundary, or the diameters. So for instance, this is a geodesic. Also, the circle orthogonal to the boundary is a geodesic, and a hyperplane, or say any plane in BD, is basically a sphere of some dimension orthogonal to the boundary sphere, or it can also be, a Euclidean plane passing through the origin, or it is a so it looks like that, right? Like a hemisphere, are orthogonal to the boundary. Okay. So these are geodesic planes in the model BD, and finally, in the upper half plane UD, we will have the following geodesics: this, and these are my planes, right? I'm dashing them just to show that this is like a surface, yeah? Or it can be a vertical plane, definitely. This is also allowed, right? So these are geodesics in geodesics, totally geodesic subspaces in UD. Okay, so what is interesting about these two models? Again, the hyperbolic angles between subspaces and like lines are the Euclidean angles between the associated sets and just RD. Also, it is interesting that the isometry group of BD or UD is generated by inversions with respect to, with respect to spheres of codimension 1, right, orthogonal to the boundary, and or those Euclidean reflections passing through the origin. Here it's the same. We can take all reflections with respect to planes or with respect to spheres orthogonal to the boundary, and those generate our full isometry group of the hyperbolic space UD and BD. Okay, the plan for the next lecture is just to discuss metrics, maybe geodesics with some more details, but usually I will just write down the formulas, maybe give some hints how to show them, how to prove them, and we will discuss the isometry groups. Since again, the hyperboloid model is very useful since the isometry group is a pretty nice Lie group. But this model gives in dimension 3 it gives another Lie group model for the isometry group, which can also be quite nice in some cases. The more global plan is so we will discuss the types of isometries in the general case, right? Again, hyperbolic, parabolic, and elliptic isometries. How do this look like in general situation, in the higher dimensions? And I think that very soon after that, we will start discrete groups of isometries and fundamental domains. So now we are moving already more really faster than before. So we spent some time on dimension 2. We'll probably get back to dimensions 2 and 3 for a while, especially when we will consider different examples of isometry groups acting in hyperbolic plane or in dimension 3. So we will kind of like repeat this again and again. But now, now it's already, so it's like, sometimes people joke that in dimension 2 is just like a standard high school hyperbolic geometry. And now it's already, we're not in a high school. We already entered the undergraduate and even a graduate program. Okay. So that's the plan for the near future. Okay, thanks.